UCSD CE 111, Lecture 7, Finite State Machine in System Verilog. Now that we've, the first one is basically basic design of basic million more finite state machine in System Verilog. But let's first think about what finite state machines bring to us. We discussed that the real design of the real circuits has to be scalable, and if you want scalability, if you have a combinational circuit, the design is going to explode if we don't keep registers or memory elements in the circuits. Basically, that inserting memory elements would help us remember some of the state of what is happening in the circuit, and then if we clock it and go to the next state, that would help us get a function done. And in fact, that's a well-known fact that only combinational circuits are typically not scalable, and we need to insert at least one memory element to call it a sequential circuit. If it's a sequential circuit, then that memory element is actually clocked by the same clock as for all the registers in the design, and every element in the circuit is either a register or a combinational logic, and the cyclic paths do not exist in combinations. So if you have a combinational circuit with a feedback loop, that's a error in the code or your design. So every time there is that, we have to save the state in the memory and go to the next one. Let's go see an example of how these things work. Here's a diagram view of how a finite state machine actually looks like. How it looks like is we have a set of inputs coming to the system, and we have a set of outputs going out of the system. And what happens in between is that in reality, the inputs get some transformation in terms of like combinational logic to generate some output logic. Then this gets stored in the state registers, and then the output is a function of what is inside the state registers. So, this goes to the output function. Some of the finite state machines are also designed to have input as being input separately and directly to the finite state machine. And this, all designs can be expressed in both ways, but if we do that, we get input directly to the output function. This is called a Mealy function, and if we don't have this connection, this is called a more finite state machine. We will see the differences in real examples. But what happens is that once you have your output and you have the state of your input, also this comes back to the next state, and you get this you basically just save the next state as a function of the current state. So this is a block diagram of the finite state machine. Let's get our hands into designing one real finite state machine and see how this actually works in practice. Here's an example of a design of a simple finite state machine. Assume that we have a tape of random zeros and ones, and then we have a snail walking down this tape, and the snail is going to go look at this tape, each of the two states, and if it sees the state 0, 1, it's going to smile. So basically, assume that the normal reaction of the snail is just something like this, and then it's going to output a smile. So the first thing is, what is the input and output of the system? So the input is every time we are going to go through this string, it's going to be, we're going to fetch 1 bit of this string. So the input is just, the input is basically the next value or the stream value of the tape. So basically the value of the tape, not just the next value. And then the output is basically the smile, right? So how many bits do we need to represent a smile? Just one bit, right? So this is, assume that this is a 1, this is a 0, and now what I'm going to do is I'm going to go through the design of a million more finite state machine. So let's think about what will happen at the reset state. At the reset state, the snail is basically just starting its venture. Let's call this S0. So, there is a reset that brings us, to say some origin of the tape, which means that at this stage, I'm going to generate kind of a poker face or a 0. So the output will be 0. And now what happens is that, let's think about the more finite state machine. Where I'm getting, the next input. So if at state S0 I get a 1, I'm not going to get any progress towards this, my goal, which is a 0, 1. So I'm going to just basically stay in this state. And now if I get a 0, I'm going to go to the next state, which I call it S1. And if I get at this S1 another 0, what will happen is I'm going to basically, stay in this same state. If I get a 1, I get to this state S2, where I'm gonna also, here the output is still 0. Here I'm gonna get the output 1. And then what happens is that if I'm at S2 and I get a 1, I'm going to come back to this state. If I get a 0, I'm going to come back to this state. So let's just call this 0, 1. And so we define this more finite state machine. How about the milli-finite state machine? Here, I have a notion of the output that is on the edge. So sometimes this helps by creating less number of states. Here, let's see how that works. So, at states S0, I have basically, the reset coming here. And what happens is that, if I get a 0, I'm going to output 0, but I'm going to go to state S1. At the state S1, if I get a 0, I'm going to still output a 0 and stay here. If I get a 1, I'm going to, I'm going to be in my original state, basically, but generate an output 1. And if I come here in S0 and I get a 1, I'm going to generate a 0 and stay in this state. So this is basically, let me just put a boundary here. So this is the more finite state machine, and this is the milli-finite state machine. Now, given these, let's just review our basic Logic 101 class, or ECE 25 in this case. What happens if you give this, to design this in real life? So we had this 2 finite state machines for the snail example that we just designed. Now let's go to the more finite state machine transition table. We had this diagram that told us we have 3 states, and if we have 3 states, then we need at least 2 bits, which means, basically the log of 3, which is a number more than 1. We need at least 2 registers to define this circuit. Okay, so we have 2 finite state machine. One is the more, the other one is milli, and because this board is very crowded, I decided to put my more finite state machine actually on this side. So here what we have is we have 3 states, so we need at least 2 registers which generate 2 to the power 2 states, or 4 states, because two states with 1 registers wouldn't be enough. So we have 2 registers here for making the circuit. And let's call this, not to confuse this S1, S2, S3, let's call this S1, S2, and S0, S1, and S2. Let's encode them with these variables that are basically 0, 0, and 0, 1, and 1, 0. So let's call S0 as 0, 0. We call this 0, 1, and we call this 1, 0. And then once we do that and we come here, we could write, the various values of the input coming in based on this chart. And then we could write the same chart in terms of a state transition table with the encodings that we just introduced. So if we do that, then, the next state will become, for example, here, if from S0 we get a 0, so from S0, if we get a 0, we go to S1, so 1 is 0, 1, and so on and so forth. So we fill up this truth table for the circuit, and here is, the encoding that we used. And once we have that, this is basically just logic 101. We are just going to take the values that are, in this registers. We are going to make the next state logic that is transforming this, and we're going to make the design. The same is true for this circuit. So here we have a finite state machine, and because it's only two states, we could determine these two states as, we can encode them with a 0 and a 1. So we just use one register, and then we could if you get a if you get a input at this S0 of 0, we get an input 0. We are going to go to state S1 and generate 0, so on and so forth. So this is basically the output of this finite state machine. So you see that there's a little bit of a difference in terms of this writing, and this was the writing style of the designer. But if you do this, the synthesis tool is going to generate one register, and in this case, it's going to generate a 2 register value. But the nice thing is, if you can express this finite state machine or a higher level description of the finite state machine in System Verilog, then the tool will go and automatically generate and optimize all these for us, which is what we are looking to learn in this class.